as people are streaming in, let's get started with our lecture today. So, welcome back to CH5010 Chemical Reactor Theory, and we are just trying to finish off our module 8, which is on ideal reactors. Okay. So, if you are talking about well mixed reactors, we have basically 3 ideal reactors, CSTR, batch and semi batch. Okay. If the system is isothermal, you only have species balance. If system is non isothermal, you will also have energy balance equations. So, when we are talking about batch reactors, there is no in and out. So, species and energy. Okay. So, species balance ends up becoming d by dt multiplied by Vck equal to Rk. Okay. If you have multiple systems. For energy balance, you have V rho Cp hat Okay. So, essentially these are what you are going to have in your species and energy balance for your batch reactor. There is no inlet and outlet terms. Okay. Now, if there is, for a number of cases that you have done before, you have only one reaction. Okay, then you will have d by dt Vck is going to be equal to nu kr, and dt by dt to r, right. So, we can use these two to basically write dt by dt is minus delta H by rho Cp hat and this from here is where we derived our T equal to T naught plus this type of an expression that we have derived because of this. Okay. So, this is just to recap. Now, what this does is basically you have now converted one differential equation into an algebraic substitution. It is not even an equation, because if you know your right hand side, you just plug in your right hand side. Once you plug in your right hand side, you can use it in this particular equation. Okay. So, this is the strategy that for a lot of cases an undergraduate you would have used. Okay. And that also gives rise to the equation that you are very familiar with, and that equation is that V batch sorry not V batch, T batch is integral d rho to x a by R a. Okay. So, these are the design equations, and these design equation, yeah, oh, yeah, Na naught V. which is Ca naught basically, or Na naught into V will go over here because it's the integral is there, right, and which brings you to Ca naught. Okay. Again, there might be some errors in the equation that I have written. Don't rely on the handwritten equations, rely on the typewritten ones and the ones in the book. Okay, this is how you derived what you did in your undergraduate. Okay. When it comes to CSTR, under steady state, you have your species balance, where because it's steady state, so you don't have d by dt term. If there's no d by dt term, you are basically going to have 0 equal to okay, and energy balance okay. This is what you get. Okay. Again, if you follow the same procedure for a single reaction, you can substitute your Rk is nu k multiplied by small r is can be replaced by delta H by Q rho Cp hat equations, or sorry, not delta H by Q rho Cp hat. You can replace small r with your Q multiplied by Ck in minus Ck, okay, and therefore you will be able to write T equal to T in plus delta T multiplied by conversion. Okay. So, what did I say just now? What I said is, if one reaction only then this equation becomes 0 equal to okay, and r multiplied by V, this guy is just going to be nu k r V, right. If this guy is just nu k r V, you can replace this with Q multiplied by Ck in minus Ck divided by nu k, Q and Q get cancelled, Cp hat. Okay. So, this is what you are going to get. You take your T on to the other side, T you take it on the other side, and you are going to get okay. This is what you are going to get, okay, which is essentially the same thing that you got from here. I had forgotten, probably I might have forgotten the nu k there. Okay. So, this is essentially what you got, and then you basically substituted in this particular equation, and when you substitute in this equation, you are going to get your V is nothing but Q multiplied by Ca in Xa divided by R or nu R. Okay. So, when it comes to your batch reactor, there is an integration involved. When it comes to the CSTR, there is no integration involved. Okay. Finally, let us come to the plug flow reactor. Okay. In plug flow reactor, we usually consider steady state. Steady state, this is 0, and therefore, you will get okay. I'm not including the heat transfer terms. Okay. So, again for single reaction, right. And of course, when it comes to calculus, this and this gets cancelled, and that is the reason why you can integrate t from t in to any location and f from f in to any location. Okay. And this is again the reason why you will get t equal to t in plus this type of a thing. So, I do not know if again I do not recall that whether nu k will be there or not there. Nu k will be there. Yeah. Again definition of delta t, yeah, nu k will be there. Okay. So, this is essentially what you are going to get. Once you get this, again the idea is that you will be able to put your t into your df by dv equation on the right hand side, and you are going to get therefore dfk by dv equal to rk of ck comma t, right. This is what leads to v equal to integral blah blah blah. Actually, so it is minus x a, right, because the df is f a naught multiplied by negative of dx a. Okay. And let us not write f a naught, let us write f a in. The reason to not write f a naught, again if you look at textbooks, they use f n, they use subscript 0 for initial conditions as well, subscript 0 for inlet conditions as well. Inlet conditions and initial conditions are different. Okay. So, if for example, when we start our reactions in our lab, let us say this is the reactor that we are going to use in the lab, okay, tubular reactor, right. So, assume that this is the tube that we are using in the lab, we do gas phase, solid catalyzed gas phase reaction. So, we will fill, you guys want to lab tour? Okay. So, how we start the reactor is, we will put the catalyst in the reactor. Okay. Chennai is very humid, so there is a lot of trace water. The trace water is in fairly large quantities. So, if we heat up the reactor like this, what's essentially going to happen is you will have water interfering, for lack of better word, with what the catalyst can do. So, the entire reactor is flushed with a diluent like argon or well, not nitrogen in a lot of cases, because nitrogen can form nitrates, nitrides in nitrates in with the catalyst. So, what we will do is we will pass argon, and in argon atmosphere we will heat it to the desired temperature. Okay. So, now the reactor contains argon. What did you want? You wanted ethane plus CO2 or ethane plus oxygen as the reactants. Okay. At time 0, you start flowing ethane and oxygen. Okay. So, at time 0, what do you have in the reactor? Okay. Why? Because everything is argon. What comes in? Or we can say partial pressure. That we are doing CO2, right? Okay. So, if we were to talk about initial conditions, your partial pressure of CO2 and ethane is 0, but at inlet the partial pressure is 0.25 bar, 0.25 bar. Initial condition, partial pressure of argon is 1 bar. Inlet condition, partial pressure of argon is half bar. Okay. When you are talking about steady state PFR, you do not take this. It does not matter. What does steady state mean? It has forgotten where you started off from. You have waited long enough for this to be forgotten. So, you have only in your courses and so on, you have only considered cases where inlet condition is what mattered, initial did not, because you are running under steady state. Okay. But when we do this in our lab, we are sometimes interested in steady state, sometimes we are interested in transients. When we are interested in transients, both the initial conditions and the inlet conditions both matter, and we will not take this to be 0. We will solve a partial differential equation. Okay. But when it comes to steady state, this does not matter at steady state. Now, how much time does it take to reach steady state? For example, in Gauri's system, it might take 1 full day to reach steady state. Okay, so we will wait for 1 entire day, so she might start the reaction today, and she'll come back tomorrow to start taking readings. Okay, she'll take 2 or 3 readings in between to make sure that nothing's gone wrong, and later on we might need that data. So, we don't want to lose that data. So, once your reaction starts, 1 hour into the reaction, 2 hours into the reaction, and maybe 8 hours into the reaction, we might take data, but really the data collection starts 1 day later. Why? Because we want to reach steady state. So, when the data collection starts 1 day later, all of these things do not matter. Okay. So, this is what we have. Okay. The problem is that when it comes to your textbooks, we are using the same variable name P0 or F0 in order to describe both inlet conditions and the initial conditions. So, that is the reason why, yeah, I mean somehow sometimes I can't get rid of how I was trained. So, sometimes I end up writing 0 and then I try to remember, oh no, this is not how I should write in and in bracket 0. So, let me just check all zeros are. See here. This is what it should be, right? Na at time t equal to 0. Okay. We do not have dearth of number of characters in English language if you do not restrict the size of the variable. So, there is no reason to just keep reusing this. Okay, coming back, this is the design equation. Okay, I am just saying UG design equation so that you can relate it. It's just a design equation. It's not, there's nothing special about undergraduate and postgraduate. I'm just trying to relate what we are doing here and the way we are generalizing for n number of species, ns species NR reaction. If we were to take a special case of one single reaction, it will come down to your design equations. Okay. There are ways in order to get equations similar to design equations when you have multiple reactions also. Okay. The main advantage of design equations today is that they allow you to do graphical evaluation of the overall system. So, you can do a kind of pictorial evaluation and then compare A versus B in a very qualitative sense. And what the qualitative comparison allows us to do is it allows us to compare against across multiple different ways of multiple different options that we want to choose between. Okay. So, if I want to choose whether I want to do catalyst A versus catalyst B versus catalyst C and all that, this particular way of thinking would be very useful or valuable in addition to your numerical stuff. Okay. What is that graphical way? This is basically your graphical way. What is that? Is if you look at the design equation, this is the design equation for your PFR. This is nothing but RA and this is nothing but RA. Okay. Or we can write this as okay. So, if you were to plot one by RA versus XA, and here also if you were to plot, or if we were to plot FA in okay, let us say we get a curve like this, and this is our desired XA, then this term is nothing but this area if this is our desired XA, then this is volume of PFR This is the volume of CSTR. Okay, and this is what essentially this slide shows. Okay, if this is F versus R, area under the curve is the volume of PFR, area of the rectangle is the volume of CSTR. If you have two CSTRs in series, you have two boxes that you draw. This is what you have done in your undergraduate, and this concept we are, and then you might have done example of a system with a recycle as well, and this is what we are going to use in today's example. Okay, so okay, this is what it requires integration of when we are plotting this versus conversion XA. Okay, how can we do the integration? This is something that in Excel we had talked about. Okay, let us say the curve is like this and you want to do this integration. Okay, you break this into multiple regions. Okay, and then connect this as trapezoids. Okay, let us call this is 0, this is XA. Okay, we will call this as A1, A2, A3, A4, A5. Okay, and we will call this as F0, this is F1, or we will call it Y. No? This value is Y1, this value is Y2, Y6. Okay, what's the area of this trapezoid? 7th standard, 8th standard stuff. It's A1 divided by 2, h by 2, sorry, or whatever, width by 2 multiplied by height 1 plus height 2. Okay, that's that area. The next area and so on. I think maybe what I should have done is okay. Usually we want A1 to A6 or the y axis to be equally spaced, right. So, we will have A1 equal to A2, So, we are just going to add up the trapezoid. Okay. This is trapezoidal rule. This is something that you have done as a part of your numerical integration. This is something that we covered in the beginning of module 3 as well. That is what we are going to use for the tutorial problem. Okay. This is what the trapezoidal rule for integration is. Okay. H is XA divided by N. XA was the desired outlet concentration or outlet conversion. You are going from 0 to XA. Okay. How many steps? 6 steps. So, XA divided by 6 was H in that example. H by 2 multiplied by y0 plus y1 plus h by 2 multiplied by y1 plus y2 plus h by 2 multiplied by y2 plus y3. So, all of the middle guys, this are coming twice, y1 is coming twice, y2 is coming twice, y5 is coming twice, y0 and y6 are coming just once. Okay. If you can remember your trapezoidal rule, great, you can use it. If you do not remember, split it up physically, just split it up into those trapezoid and calculate those individual areas. Those calculations are not any more difficult than the other calculations. It involves 2n additions, 1 multiplication, 1 division. That is all, irrespective of which way you do it. Okay. That is what we are going to use in this particular example. Okay. Now, the fun thing is whether it is CSTR or PFR, if you realize T equal to T naught plus delta T adiabatic equation was the same, right. So, how are we going to solve this? Determine the exit temperature if exit concentration was 4 moles per liter. Your T out or T at any time right. I think. Okay. Again, I might have made if there is a minor mistake, then just correct it. Okay. Now, delta H is given, Q rho Cp are given, Ca in multiplied by Q is given. So, minus delta H and that is basically going to be the same as yesterday. Okay. Why do you think it's same as yesterday? why irrespective of CSTR, PFR, batch, your delta T adiabatic has the same expression? Yes? Okay. 2-3 different ways of answering this. One is basically the thermochemistry is the same, which basically means the thermodynamics is the same. Okay. Delta T adiabatic talks about what's the maximum temperature you can reach if all of the species got converted. Okay, so delta T adiabatic is the end point or the max point that you can reach under adiabatic condition. It's a thermodynamic constraint. If you are a chemist, it comes from your thermochemical properties. If you are a chemical mechanical engineer, it is a thermodynamic constraint. Okay. If you are just entering your second year in chemical engineering, okay, this comes from your process calculations. Where did you draw the box around process calculation? You never thought about what reactor it is, right? You drew your process calculation box around this. Okay, this is in, this is out, this is in, this is out. You didn't bother how those transformation was taking place. It's a single reactor, 10 reactors, tubular reactor, none of that. Remember how did you do it? Boxes, not reactors in your process calculation. So, if you are to think all of your reactors as boxes, the overall energy balance around that dabba remains the same, and that dabba is the same dabba. That is the reason why, that is a third explanation why your all three reactors, your delta T adiabatic turns out to be the same. Okay. Whether you want to think about it from your chemistry background viewpoint, whether you want to think about it from thermodynamics course viewpoint, or whether you want to think about it from process calculations viewpoint. In reality, they are all the same. We made those silos so that as new students in chemistry or chemical engineering, you could understand the subjects. Okay, nature does not know those silos. Nature does not know that it has to follow thermodynamics laws. No, it is the thermodynamics laws that are made to explain observations in nature. So, it is the other way around. Okay, so the nature does not care what laws we made. The nature follows its laws, and we have made those laws in order to explain what is happening in the nature, not the nature. Okay. So, that is where you get delta T adiabatic. Okay. So, if you have delta T adiabatic, you can put in conversion. Yeah. Exit. Yeah. Right. Volume of PFR. Okay. So, from here okay, RA is this guy, Okay. This all is denominator. Okay. And this you can integrate it using the trapezoidal rule. Okay. This integration using Excel is what we will do in tomorrow's class. This integration using hand calculations for a slightly different problem is what you are going to do as a part of your assignment.